Okay, today we're going to look at Chapter 1, Functions. We're going to look specifically at Section 1.1, Functions and Function Notation. So, determining whether a relation represents a function. So a relation is basically a set of ordered pairs. And so, we've got this set of ordered pairs, they're x, y, so you have 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. And we have things called domains and ranges. I'm sure we've seen those before in other classes. Well, a domain, that's the set of the first component, or your x component, basically your x values. And these are going to be your input values. So looking at this set of ordered pairs, our x values are 1, 2, 3, 4, and 5. Then our range, that's the second set of components in each ordered pair, which is basically our y values. And so the y values, the range is basically going to be 2, 4, 6, 8, and 10. And so, we say it's the set 1, 2, 3, 4, 5 for the domain, and the set 2, 4, 6, 8, 10 for the range. Now, a function is any relation in which each possible input value leads to exactly one output value. So you put in something and you get exactly one thing out. And the output then is a function of that input. So what we're going to do is we're going to show some examples of things that are functions and not functions. And so let's say we have the domain hij and the range lmn. Okay, so we could have input hij, and we could have the output lmn. And so to be a function, each one of these is going to map to exactly one output. And so that would be how we could get this to do that as far as a function goes. Now, another way we could do this is we could say, well, we have hij, but let's say we only have outputs L and M. Okay, well, H could go to L, I could go to M, and J could also go to M. Now this is a legitimate function because each input is going to exactly one output. So it can go to the same output, but it's going to exactly just one output. Now, when is it not a function? Well, let's kind of look at this going backwards off of this one here. So let's say we have the input now instead of being output. Let's call this L and M, and our output now is H, I, J. Then what if we go with kind of the opposite of what we have here? We just swap it around. The L goes to H, the M is going to go to I, and the M is going to go to J. So here we have an input going to two outputs, and so that is not a function. So we can go two different ones going to the same one this way, but we can't have one going to two different ones this way and be a function. Okay. Now, how to determine a relation between two quantities and determine whether a relationship is actually a function? Well, first you have to identify your input values. Then you have to identify your output values. And then if each input value leads to only one output value, then the relation is a function. Now, if it leads to two or more outputs, then it's not a function like we just saw in that example before. So what we have here is we have a set of XY ordered pairs, and it's going to be 5, 3, 10, 8, 15, 8. Now it says, does the relation in the table form represent Y as a function of X? Okay, well, if we do that, this is going to be our output, this is going to be our input. So, that goes to exactly 1, that goes to exactly 1, and that goes to exactly 1. So yes, it is a function in this form. Now, what about this one? Of x as a function of y. So now this is going to be our input, and this is going to be our output. So we're going the opposite direction. So now when we go the opposite direction, 3 goes to 5 is fine, 8 goes to 10, and 8 goes to 15. Now remember, those two 8s are the same 8. They're not different. And so what we could have done is we could have redrawn this as x, y, and we could have said, well, 5 to 3 and 10 to 8. Oops, 8, not 10. And so that's an 8, and we could have said 15 to 8, and so we could have drawn that other thing like this instead. And so then when we go the other way, y to x, we have 3, we have 8, and we have 5, 10, and 15. And so 3 goes to 5, 8 goes to 10, and 8 goes to 15. So this direction, this one is going to 2 outputs, which is not a function. So that one is no. So it's not going to be a function of y. Okay, so again, you can write it like this, or we could have changed it and rewritten it with them both going to the single 8, and then that single 8 going to the 2 there. It makes it look a little more understandable that that 8 is the same 8. Now, function notation. Once it's determined it is a function, we write a relationship into function notation. So if we have a true function, what we're going to do is we're going to replace y with f of x. And so the function is named f of x and read as y is a function of x, where x is in the input value, and y or f of x is the output value. So again, these two are the same, so these are both outputs, and then our input is that x value there. So one other thing to note is we can use any letter for basically our function name. We could use, A, B, C, D, E, whatever, and I've even seen it where, they have x of x, and so you have to represent, figure out which x they're talking about. One's usually a large x, one's a small x or something, but you could even do that as well. But usually it's, F, G, H, and that region there that we use as our function letters. But again, it doesn't matter. Any letter can be used. All right, so this is an example here, and it says the amount of garbage G produced by a city with population P is given by G equals F of P. Now remember, G is going to be equal to your Y, and then that's just your function F of P. And G is measured in tons per week, and our P, which is the population, is measured in thousands of people. So instead of saying 40,000, we're going to call that 40, and we know it's in thousands, so it's going to be 40,000. All right, so it says the town of Tola has a population of 40,000 and produces 13 tons of garbage each week. Express this information in terms of the function f. Okay, so what we want to do is we want to rewrite this with the given information here in part A. Well, so part A says we produce 13 tons of garbage, and G is tons of garbage produced per week. So we're going to say, well, 13 equals, and now we have f of the population. Well, the population is 40,000, but remember we do it in thousands, so all we're going to do is 40. So that's the f of 40, and that is going to be our function notation for this part A. Now part B says, explain the meaning of the statement f of 5 is equal to 2. All right, well, what does that mean? Well, here 2, remember, is going to be tons of trash per week, and 5 is going to be in thousands of people. So it's going to say 5,000 people produce 2 tons of garbage per week. Okay, and so that's what the interpretation of f of 5 equals 2. So we're having 5,000 people and they produce 2 tons of garbage. All right, so how do we evaluate functions? Well, we evaluate functions. First, you know the input value, and you plug that into whatever the function is, and then you have to solve for the result. And if you know the output value, basically you set the output equal to the function formula and then solve for the variable that's left. So, most of the time it's x, but it could be anything, t or whatever. And in this case, when you do it this way, you might get more than one solution. So what we're going to do first is we're going to evaluate the functions, and basically we want, this is our function, f of x equals 6x minus 1 over 5x plus 2. We want to find f of negative 3, f of 2, f of negative a, minus f of a, and f of a plus h. All right, so what we do is we just plug in our input in place of the x, and so whatever our input is, we change that here. So what we're going to do is say, and we're going to probably have to have 2 pages here, f of negative 3 is equal to, well, that's going to be 6 times negative 3 minus 1 all over 5 times negative 3 and then plus 2. Okay, and so I guess I don't really need that parenthesis on the end here. So now we take 6 times negative 3, that's negative 18, then minus 1 over, that's going to be negative 15, then plus 2. And so negative 18 minus 1 is negative 19, and minus 15 plus 2 is going to be minus 13. And negative divided by negative is positive, and 19 and 13 are both primes, and so we can't reduce it. And so that would be the evaluation of this f of negative 3. All right, so now let's do f of 2. So f of 2 is equal to, well, we'll have 6 times 2 minus 1. Then we'll have 5 times 2 plus 2. Well, 6 times 2 is 12 minus 1. 5 times 2 is 10 plus 2. Well, 12 minus 1 is 11. 10 plus 2 is 12. And so we get 11 twelfths as our answer. All right, so now we need to go to the next page and do f of negative a, negative f of a. Well, negative f of a is going to be pretty easy. We just are going to plug in a instead of x, and we're going to change the sign. And then the a plus h, we have to plug it in, multiply, and distribute. So we'll have a little bit more work there. So maybe we could get f of a on this side still and have a little more room, f of negative a. So we have 6 times negative a minus 1 over 5 times negative a plus 2. Well, that's going to give us a negative 6a minus 1. And then here we have a negative 5a plus 2. And if we think about this, we can't simplify in the numerator, we can't really simplify in the denominator, and so therefore what we can do is not too much. Trying to think if we want to do anything, because we have, you know, 2 negatives here, maybe we could change a sign, but I think, you know, at this point we really could just leave it as what we have it, and we're good to go there. So now we just have negative f of a, so we have to do negative f of a, and the other one I think was f of a plus h, if I'm correct. Yep. And so 6x minus 1, write this over here, all over 5x plus 2, I believe. Yes. All right. So what we're going to do here is we're going to plug in a, and we're going to have the sign negative. So we're going to take 6 times a minus 1 over 5 times a plus 2. And then we just change the sign. And so I'm just going to take that negative and distribute it across the top. And so negative 1 times positive 6a is going to give me negative 6a. Negative 1 times a negative 1 here times a negative 1 here is going to be plus 1. And then we still have 5a plus 2 in the denominator. And so that would be what f of a when we take the opposite of it. Okay. Now if we plug in a plus h, that's going to be 6 times a plus h minus 1 all over 5 times a plus h plus 2. So then we have, well, we have to distribute here, and we're going to have to distribute here. So in the numerator, we have 6a plus 6h minus 1. The denominator will have 5a plus 5h plus 2. Okay. And so at that point, that's about as far as we can go, and so that would be then our final answer, because we can't simplify. We have a's and h's and 1's, and here again nothing simplifies, and so we would just leave that as our final answer. All right, given the function h of x is equal to the square root of x minus 3, solve for h of x equals 3. So this one, instead of plugging in for the 8 or the x, we're going to substitute for the y. So this really is equal to y, and so we're going to say 3 equals the square root of x minus 3. So we're plugging in the 3 in place of our h of x. Okay, so kind of the opposite of what we just did. And so when we do that, what we have to do is we have to solve for x. Well, to be able to solve for x, we have to get rid of that square root. So what we have to do is we're going to have to square both sides. So 3 squared is 9. And when we take the square root and we raise it to the power 2, that just drops it. And so then we have x minus 3. Now we add 3. And so 12 is equal to x. And so that basically is our solution. X is equal to 12. And that's all we have to do. And if we plug in 12, subtract 3, that's 9. Squared and 9 is 3. And so that works. All right, so if we're given a function in equation form, what we want to do is write it into an algebraic formula. So what we have to do is we have to solve the equation to isolate the output variable on one side of the equal sign, with the other side as an expression that involves the input variable. And then we use all the usual algebraic methods to do that. So we add or subtract the same thing on both sides, we multiply or divide the same things on both sides, and we get to the point where we get our actual values on the right side that they're supposed to be on. And so what we're going to do is we can consider this equation relationship. 3r plus 2t is equal to 18. And what we want to do is write the relationship as a function where r is equal to f of t. So basically that means we want to solve this here piece for r. So that's going to be our first thing. Once we solve it for r, we're going to replace that r with f of t. All right, so let's first solve for r. So we have 3r plus 2t equals 18. Well, if I want r over here, I got to get rid of the 2t. So that gives me 3r equals 18 minus 2t. Now to solve for r, I have to divide by 3. And so r is equal to 18 minus 2t all over 3. Okay. Now that's r, but now it says, okay, replace r with f of t, so that means f of t is equal to 18 minus 2t all over my 3. Now the next one says, okay, well now that we've got that, let's find what f of negative 3 is. So basically we're saying take t as negative 3 and plug it into here and simplify. So next column here we have f of negative 3, that's equal to 18 minus 2 times negative 3 all over, and then we had a 3. Well, here a negative 2 times a negative 3 is a plus 6. We have 18 plus 6 over 3. And so then 18 plus 6 is going to give me 24 over 3. And 24 divided by 3 is 8. And so that would then be my solution there. And so this is kind of the first piece. And then f of negative 3 is equal to 8. All right. Now the next one says, okay, well, f of t is equal to 2. So what we're going to do is we're going to replace f of t in our original function with 2. So 2 equals, then we have 18 minus 2t all over 3. And what we want to do is we want to solve. And what that means is we have to solve for what's left. Well, what's left is that t. So we have to get rid of everything on this right side except for t. So first, we'll multiply both sides by 3. Okay. Now we have basically a subtraction. So what I'm going to do is I'm going to get rid of 18 here. And so what's going to happen is I'm going to have to end up dividing by a negative 2, but that's okay. So negative 18 plus 6 is going to give me a negative 12, and that's equal to negative 2t. Now I solve for t, so I have to divide by a negative 2. And so what does that say? Well, t is negative 12 divided by negative 2, which is 6. And so that then is my solution. So first we had to solve our equation for the variable that they ask us to solve for, in this case r, replace the r then with f of t, get our function, and then we evaluate f of negative 3 by plugging in negative 3 in place of t, and then the other one we had f of t as 2, so we replace the f of t with 2 and solve for our t. All right, so the next one, does the equation x squared plus y squared equal 1 represent a function with x as the input and y as the output? Well, what does that mean? Well, we have to solve x squared plus y squared equals 1 for y. So if we do that, we have to subtract x squared. And so we have y squared equals 1 minus x squared. Now, to get y by itself, which is how we need to do it, to get it to look something like this, we have to take the square root. Now remember that when we take the square root here, that's fine. But when we take the square root on this side, we have to take plus or minus because both of them could give us the answer here. Okay, so we have plus or minus the square root. So that says y is equal to the square root of 1 minus x squared, and y equals negative square root of 1 minus x squared. Okay, so that means if I plug in one value of x, say I plug in, I don't know what value I want to plug in here, but whatever I plug in, I get this two different outputs. It's going to be, one value is going to give me two different things. I'm going to get a positive one and I'm going to get a negative one. And so this is not a function. Okay. And so that's the key here, is when you get the one value of x plugged in here, you're going to get a positive square root of it and you're going to get a negative square root of it. Okay, so that's why it's not a function. So you have to really pay attention to what your input is and then what your output is. All right, so this one is if we're given a function as a represented by a table, what we need to do is we need to identify specific output and input values. So if we're given an input in the row or column, sometimes they give them in, the rows like we have here. Sometimes they're in columns like we had in one of them had, 3 in a column. What we have to do is we have to find the input value and then identify the corresponding output value pair that's with that input value, okay? Or if we're given an output value in the row or column, now key thing here is you have to know every time that output appears. So it may be multiple times for the output, because remember, we could have 3 going to 8, and we also could have 5 going to 8 and still be a function. Now we can't go the other way and have a function, but going this direction we can have a function. And so therefore we may have multiple times that the output is going to be viable. And then after that we have to identify what the input values that are corresponding to the given output. All right, so this one says evaluate f of 4 from this table. Well, that means x is going to be what 4 is. So we look for x, we go over to 4, and so that's our 4. And then we go down to find what f of 4 is, because now we're saying f of 4 is equal to 56. So that then is our answer to that one. Now we're going to go the opposite direction. We're going to do this OR part. And it's going to say solve f of x equals 28. So now we have to go across here and find 28. All right, so there's 28. Now make sure there's no more. Oh, there's one there. So that means there's 2 f of x's that equal 28. And now what we want to do is we want to solve for x. So x is going to equal, well, if this is f of x, x is going to be 1, or in this case, it could be 9. So you have 2 solutions in this case. So x is 1 or x is 9. Whereas in the first one, you're plugging in one specific x and you're going to only get out one specific value for your f of x, which is equal to basically your y. So don't forget that's just equal to y. Okay, so inputs and outputs. So being able to figure out what your input is and then also what your output is in a table is very important. You can also do it from a graph, so finding function values from a graph. So it works the same as the table, but you have to read your values from the graph itself to find both the input and output values. Now, it's easier to find duplicates in this matter because it's going to be a lot more visible, and this one is an example where there is duplicates, and so it kind of shows you how much easier it is, because here, you had to really go across and look in all the different values, and then you found the 228s, whereas this one you'll see it's a little bit different. All right, so here we want to evaluate f of 0. So this means x is equal to 0. So f of 0 is equal to what? Well, if x is equal to 0, the output is 1. Okay, and so f of 0 is equal to 1. So that one's pretty easy. You just have your x value, plug it in, and then you get your y out, which is, this case, 1. Now this one, we're going to solve for f of x equals -3. Remember, that means y is equal to a -3. So if you ever have issues with what is f of x, that's equal to y. And so that's your output. And so when y is -3, well, y is -3 at this point. And this is why I say it's easier to see in a graph because you can go straight across looking easy. You don't have to go through a lot of numbers, and you can see that y is -3 here and y is -3 here. And what are the x values? Well, here x is equal to what? Well, it's going to be -2 for that first one, and x equals on this one, it's going to be a +2. Okay. And so that's how we can do it with a graph. So we've looked at tables and graphs and the function. And so those all the different ways we can actually solve things depending on what they're asking us to do and what they actually give us to do for the problem. Now, we can also look at a graph and determine if it's actually a function using something called the vertical line test. I'm sure you might have heard this before. It's pretty common. Basically, you're just going to inspect the graph to determine if there's any vertical line that can be drawn that intersects a curve more than once. Now, if any line exists that intersects it more than once, then the graph is not a function and basically you're done. But if it doesn't and you just get one point it crosses every time you look through the whole graph, it only crosses one time, then the next thing to look at is, well, is it a one-to-one function? What does that mean? Well, if a function in which each output value corresponds to exactly one input value, then it's going to be one-to-one. So once we know it's function with the vertical line test, then we're going to move over to the horizontal line test to determine if it's one-to-one. So kind of think about vertical line. We draw a vertical line through it, and if it intersects only once, it's a function. Well, the same thing happens here. If you can draw a horizontal line through the graph only once, then it's going to be one-to-one. But if you find a place where it intersects more than one time, then the graph is not one-to-one. So really kind of simple, just drawing lines. You don't even actually have to draw them. You just kind of look and see. And what we're going to do now is kind of use the vertical line test followed by the horizontal line test. So first, we're going to see which ones represent a function. So drawing vertical lines. Well, if we draw a vertical line through here, think about all these vertical lines here. How many times do they hit this graph? Well, they only hit it once. So is it a function? Yes. Okay. What about this one? Well, guess what? Boom, we hit it twice already and we didn't even do anything really. So that one is not a function. And because it's not a function, we don't even have to worry about this second one. All right, so here, what about this one? Well, here, guess what? We hit it twice, and so it's not a function either. What about this one? Well, if we look at all those vertical lines through there, only hit one time, and so yes, that one is a function. All right, same thing here. No matter how many times we draw a vertical line, we hit it only one time, so that is a function. And finally, on this last one, again, no matter how many times we draw vertical lines, we get it is a function. Now is a one-to-one function is the key. So now if we draw a horizontal line, now we look at our lines going this way, well, guess what? That hits like 3 times. So no, that's not one-to-one. So we can say not one-to-one. We don't have to worry about that one, and we don't have to worry about that one. Now this one, well, here, no matter how many we draw, yeah, that is one-to-one. Now this one, if we look right away, boom, it hits twice. So that one's not one-to-one. Now going back to this last one, no matter how many times we draw a line. Now remember, this goes all the way up to that x-axis, but it never touches it. And this one comes all the way down almost to the x-axis, but never touches it. And so this is not going to intersect it. And so yes, this is one-to-one as well. Okay, and so that's kind of how you tell the function as well as if it's a one-to-one function. So you use the vertical line test first and then the horizontal line test second. All right, so now what I want to do is talk about the toolkit functions. So in this class, we're going to use these functions quite a bit. And so kind of learning the table 13 on page 16 and 17 is going to really help you through this semester. So let me find my book here. And so this is going to be the table, and again, it's page 16, and that's toolkit functions. So, we have like the constant function, so you just have a straight line, what it is. Here we have the identity function, which is just that line y equals x. And then we have absolute value functions, so it ends up giving you this v-shaped function. We have the quadratic, which you know is a parabola. We have the cubic function, so it comes down and over, and that's what that one's going to be, so it's some x cubed. We have the reciprocal 1 over x, so that was that last one we looked at that was 1 to 1. The reciprocal squared, which we found out was not 1 to 1. It was a function, but it's not 1 to 1. We have the square root function, and remember, it's going to only be the positives because you can't put a negative under the square root, otherwise it's going to be imaginary, and so we don't have a piece come down here, it's only a piece going up there. And then we have the cube root, and so then we have, again, that one there, and that was, I think, one of the first ones that was a function as well as 1 to 1. So those are all the functions I think you need to kind of be aware of, because we will be using these a lot. We'll be transforming them, changing them, you know, maybe it starts here, but all of a sudden we move it over here and flip it upside down. So we're going to look at transformations, and so starting to learn these functions will help you. All right, so that's all I have for section 1.1.